Okay, let's unpack this a bit.
Yeah.
We all feel gravity, right? I mean, constantly.
Every second.
It's this invisible hand keeping us on Earth, keeping planets, doing their dance.
And dictating the tides, everything.
And for ages, you have minds like Newton and Einstein giving us these incredible tools mathematically to describe how it works. Stunning precision, really.
And they were fantastically successful. Newton's laws, universal gravitation, describing it as a pull between objects.
Right.
Then Einstein comes along, refines it with general relativity, says gravity is, well, the warping of space-time itself.
Both models, fantastic description.
You really are.
But here's the mystery that just wouldn't go away, even for them.
Mm-hmm.
What is gravity, fundamentally? What's the cause?
Exactly. How does it work across these huge distances of what looks like empty space?
That action at a distance thing, it's a paradox.
It is. And that's really the core mystery that the source material we're looking at dives into. It takes us through the history of how we've thought about this.
And proposes a new way.
A pretty fascinating, kind of novel way to think about not just gravity, but also inertia. That resistance you feel when you speed up or slow down.
Yeah, that pushback.
And even the nature of space itself.
Okay, so our mission here in this deep dive is to explore these sources, see how they challenge our usual picture, suggesting gravity might not be like a fundamental thing after all.
Maybe something else entirely.
And it kicks off with that really old question, is space really empty? Or is there something in the nothing?
Precisely. Philosophers argued about the void forever. Can true nothingness even exist?
Takes you back.
Yeah, think ancient Greeks. The Stoics thought space was filled with pneuma, like an energizing fluid.
Huh.
Empedocles talked about an ether, not matter, not nothing.
And Plato had his quintessessentia, right? The fifth element.
Linked it to geometry, the Platonic solids. He saw it as this perfect eternal substance making up the heavens, the fabric of the void itself.
And there's that weird connection mentioned in the source about his focus on triangles echoing modern quark structures.
It's a strange resonance, isn't it? Protons, neutrons, built from triplets of quarks, often represented with triangles, thousands of years apart.
Wow. But the idea of emptiness was powerful, too. The atomists needed it.
Oh, absolutely. Their little indivisible particles needed space to move in. Otherwise, everything's just jammed together solid.
No movement possible.
But then Aristotle pushed back hard. Nature abhors a vacuum, he famously said.
Right.
His view was, if you somehow made a void, something would instantly rush in, implying space was never truly empty, always made of something.
So this debate, something versus nothing, it just kept going, right up to Newton.
It did. Newton gave us the how, the math of gravity. Objects attract based on mass and distance, but not the why. Still that action at a distance mystery.
He wasn't happy with it, though, was he?
Not entirely. He actually did speculate about an ether himself, a medium to transmit that pull.
But he had a snag.
A big one. If space is full of this fluid-like stuff, how do planets keep orbiting forever? Shouldn't they slow down, lose energy, spiral into the sun?
Yeah, friction, basically. The medium needed for the force would stop the motion.
Exactly. He even played with another idea, less famous, in his book Optics. Maybe gravity was like light bending through a lens.
An optical effect.
Yeah, caused by changes in ether density. Objects would just follow curved paths because the medium itself was, well, uneven.
Interesting. Like a mirage.
Sort of. But ultimately, Newton backed off explaining the cause. He stuck to the math.
I feign no hypotheses.
Pretty much. Describe what you can measure, accurately, and his math worked incredibly well.
And that held for a long time. But the ether idea came back.
Big time. Especially in the 19th century with James Clerk Maxwell.
Unifying electricity and magnetism. Light.
Exactly. Maxwell showed light is an electromagnetic wave. And waves, well, they usually need something to wave in.
Like sound needs air, ripples need water.
Right. So they proposed the luminiferous ether. A substance filling space just for light waves to travel through. It fit the whole mechanistic industrial age view of the universe as a giant machine.
It felt logical, necessary, but then came the experiment that changed everything.
Michelson-Morley, 1887. A truly pivotal moment.
What was the idea behind it?
Pretty straightforward, actually. If Earth is moving through this stationary ether, like a ship through water, we should detect an ether wind.
Meaning?
Meaning the speed of light should look slightly different depending on which direction you measure it going with the wind, against it, across it.
Okay. How they test that?
They used a clever device, an interferometer. split a beam of light, sent the two halves along perpendicular paths, bounced them off mirrors, and brought them back together.
Looking for interference, like ripples canceling out or adding up.
Exactly. If one beam was slowed down or sped up by the ether wind relative to the other, the light waves wouldn't line up perfectly when they recombined, creating a specific interference pattern. Similar idea to Young's double-slit experiment.
And the result?
Nothing. Absolutely nothing. No shift in the interference pattern, no detectable ether wind.
Wow. One of physics' great null results.
A huge one. It was a major blow against that specific idea of a mechanical, stationary ether that light travels through.
And it set the stage for Einstein.
It really did. It opened the door to his radical idea. The speed of light is constant for everyone, no matter how they're moving. The mechanical ether just wasn't needed.
Which, funny enough, brings us back around to Einstein and general relativity, GR, about 200 years after Newton, roughly.
And GR was another massive leap. It ditched Newton's mysterious force for this incredibly elegant geometric picture.
Right. Instead of a pull, GR says matter and energy actually curve the fabric of spacetime itself.
And objects aren't pulled. They just follow the natural paths, the geodesics, through this curved landscape.
The classic analogy is the bowling ball on a rubber sheet, right?
That's the one. It makes a dip, and a Mario rolling nearby curves towards it, following the contours of the sheet, not because the ball is pulling it directly.
And GR is incredibly successful. Predicts black holes, explains Mercury's weird orbit perfectly.
Solved Newton's action at a distance problem, too, by making gravity a local consequence of geometry. It's all about the shape of space-time right here.
But, and it feels like there's always a but.
There often is in physics.
GR tells us how space-time curves and how things move in it, but
Yeah.
What is this space-time fabric?
Exactly. How can nothing have a shape? How can it be warped? And how do objects know it's warped and react?
It brings the ether question back in a different form.
It does. Einstein himself knew this. Even after GR, in 1920, he said something like, "Space without ether is unthinkable." GR needs some kind of underlying medium or manifold, even if it's not the old mechanical one.
So the sources we're looking at really hammer this point home. GR's curvature is mainly a powerful mathematical description.
A brilliant description of gravity's effects, yes. But it doesn't necessarily give us the physical cause. It tells us how things behave gravitationally, maybe not fundamentally why.
Okay, so mystery remains. Let's shift gears then, from the huge scale of GR down to the tiny scale of quantum mechanics, because QM has a very different take on empty space.
Oh yeah, this is where it gets really, really weird and interesting. QM says the vacuum is anything but empty.
Not empty.
Not at all. Think about tuning an old analog TV between channels, all that static, that snow.
Yeah.
That's actually amplifying quantum vacuum fluctuations. The QM vacuum is this seething, chaotic ocean of energy fields popping in and out of existence constantly. Energy's always there. You can't pump it all out.
So it's like a baseline energy level for the universe.
Sort of a 0-point energy, yeah.
Yeah.
It's fundamental. And it's not just theory.
There's proof.
Experimental proof. The most famous example is the Casimir effect.
Okay, tell me about that.
Predicted back in the 40s, measured definitively much later. The setup is conceptually simple. Take two perfectly smooth, uncharged metal plates and put them incredibly close together in a vacuum.
Okay.
The theory predicted they should actually be pushed together by a tiny but measurable force.
Pushed together by nothing. That sounds backwards.
By the vacuum. See, the plates act like boundaries for those quantum vacuum fluctuations, those energy waves. Between the plates, only certain wavelength of the vacuum energy can fit, basically. Waves that have nodes at the plates, like harmonics on a guitar string.
Ah, okay. So it restricts the possibilities between the plates.
Exactly. But outside the plates, in the wider vacuum, all wavelengths are allowed. So you end up with a higher energy density, effectively higher pressure, outside the plates compared to between them.
And that pushes them together.
Precisely. It's been measured. It proves the vacuum isn't just empty stage, it's a dynamic plenum of energy, and it interacts with matter.
That's mind-bending. Okay, so the vacuum is real, it's energetic. Now, how does this connect to inertia?
Right, inertia, that feeling you get, that resistance when you accelerate. Hit the gas, hit the brakes, take a sharp turn.
You feel it instantly, locally,
No.
right where you are. Doesn't matter if you're in a car or, hypothetically, accelerating a spaceship in deep space.
Exactly. So if space were truly empty, where does that instant local resistance come from? It's a deep question.
Did anyone try to explain it before?
Oh, yes. Ernst Mach, late 1800s. He had this idea, Mach's principle. He suggested inertia isn't inherent to an object, but arises from its interaction with all the other matter in the entire universe.
Like a cosmic web. Everything connected gravitationally?
Sort of, yeah. He drew analogies like with the Doppler effect, how sound or light waves shift frequency based on relative motion, like
Right.
the red shift of distant galaxies showing the universe is expanding.
Okay, but what was the problem with Mach's idea?
The main issue was, if inertia is about this connection to distant stars via gravity, why do you only feel it when you accelerate? Why not when you're just moving uniformly?
Good point. Cruising at a constant speed feels the same as being still, but acceleration,
Yeah.
you feel that.
You definitely feel that force. Which brings us right back to the equivalence principle.
Galileo, Einstein,
Mhm.
the idea that the force you feel from acceleration is fundamentally indistinguishable from the force of gravity.
Yep. Galileo's maybe apocryphal Tower of Pisa experiment, or the real one on the moon feather and hammer falling at the same rate. Gravity accelerates all mass equally.
And Einstein's thought experiment. The elevator.
The windowless elevator, right. Can you tell if you're sitting still on Earth feeling gravity or accelerating upwards at 9.8 meters of space feeling inertia?
No. They feel identical.
Gravity is acceleration, or rather, they are equivalent experiences.
So the pushback you feel when your car speeds up is the same kind of phenomenon as the weight you feel standing on Earth.
Fundamentally, yes. And GR explains this geometrically. Inertial force is what you feel when you resist following a natural geodesic path through curved spacetime.
Like if you're in free fall, you're following a geodesic, you feel weightless,
Yeah.
no inertial force.
Exactly. But try to stand still on Earth or accelerate in a straight line through curved space, you're deviating from that natural path and you feel resistance.
And there are even analogies suggesting GR's geometry might have a physical basis, like fluid dynamics.
Yeah, physicist William Unruh and others showed you can model things like black hole event horizons using fluid analogies. Imagine water flowing towards a drain faster than the speed of sound in that water.
Sound waves couldn't escape upstream.
Right, it's like an acoustic black hole. It suggests these weird GR effects might not just be abstract math, they could correspond to physical processes, perhaps in the vacuum itself.
Okay. And one more piece. EMC shape.
Yes. Crucial. Not just mass can be converted to energy, but mass is energy. They are equivalent.
And energy is related to work, to change, to acceleration.
Precisely. It takes energy to accelerate a mass. The more massive something is, the more energy it takes, the more inertia it has. Mass is essentially a measure of an object's inertia, its resistance to acceleration.
It's like mass is the amount of energy locked up that resists being changed.
That's a good way to put it. It's the system's resistance to changes in its state of motion.
So let's tie this together. We have inertia, this very real local force you feel instantly when you accelerate. We have the equivalence principle saying inertia and gravity are two sides of the same coin. And we have the quantum vacuum, this energetic, physical something that fills all of space.
It really starts to point towards the vacuum, doesn't it? If inertia arises locally and instantly, maybe it's an interaction with this local vacuum energy field.
And if inertia and gravity are equivalent, maybe gravity is also an interaction with the vacuum.
That's the logical leap.
Yep.
It strongly suggests the vacuum isn't passive. It's actively involved in causing both phenomena.
Which leads directly to the core idea in the source material we're exploring.
Yes. The proposition that maybe gravity and inertia aren't fundamental forces at all.
Byproducts.
Byproducts of something else entirely.
And this something else is tackled by this electrogravimagnetics model, EGM.
Right. EGM proposes a really different picture. Forget curved geometry as the fundamental thing. Think of space-time or the vacuum as acting like a refractive medium when matter is present.
Refractive. Like light bending through glass or water.
Exactly like that. The idea is that matter, which is mass energy, is constantly interacting with the quantum vacuum, doing work on it, exchanging energy, and crucially, the EGM model proposes this fundamental energy exchange is electromagnetic in nature.
So, gravity is the result of EM interactions between matter and the vacuum.
That's the claim. Gravity is presented as an emergent byproduct of this ongoing EM exchange. Things like planets and light rays follow the paths they do not because space-time is geometrically curved, but because they are being refracted as they move through this vacuum medium whose refractive properties are altered by the presence of mass energy.
So it's an optical phenomenon, fundamentally.
In this view, yes, it produces the same effects as GR, the same paths, but interprets the cause differently as refraction, not geometry.
And EGM is presented as an engineering tool.
Yeah, the sources describe it less as pure theoretical physics and more like an engineering approach, taking known principles, especially electromagnetism, and applying them inductively to sort of reverse engineer gravity. How could gravity work if it's fundamentally electromagnetic?
And it shows how GR and QM might be linked.
It aims to bridge that gap, suggesting they both stem from this underlying EM interaction with the vacuum. A single principle working from subatomic scales right up to cosmology.
And the name of the source series, Quinta Essentia.
Deliberately echoes Plato's fifth element, his ether. The suggestion is clear. The quantum vacuum is the modern understanding of that fundamental substrate, that fabric of reality.
Okay, so for you listening, trying to get those aha moments, if inertia, that feeling of resistance, comes from a real physical interaction with this vacuum fabric.
Then maybe, just maybe, that interaction could be manipulated.
If you could affect the vacuum, could you affect inertia?
That's the tantalizing possibility. And if you could affect inertia, remember the equivalence principle. Affecting inertia implies affecting gravity.
It brings to mind Archimedes, right? Give me a firm place to stand and I shall move the earth.
Exactly. If you could somehow control or negate inertia by manipulating the vacuum interaction, maybe you could gain that firm place to stand relative to the universe itself. The implications are, well, enormous.
So, quite a journey. From ancient Greeks wondering about empty space, through Newton's force, Einstein's geometry, the weirdness of the quantum vacuum, the mystery of inertia.
All leading to this perspective, EGM, that tries to unify it all by suggesting gravity and inertia are basically electromagnetic effects stemming from matter's conversation with the vacuum.
The big aha here seems to be, maybe the forces we experience most profoundly, gravity and inertia, aren't the fundamental building blocks. Maybe they're emergent properties.
Like wetness emerging from water molecules or temperature from molecular motion. They're consequences of deeper interactions.
So a final thought to leave you with. If this picture holds any water, if the physical vacuum is the source of inertia and gravity, and that interaction is electromagnetic, what does it really open up?
Forget just moving things or counteracting gravity. If you could truly engineer the vacuum itself, what new physics, what new technologies, what new understanding of reality might become possible? What happens when you can tweak the fabric of nothingness?